Hi everybody, this is going to be a video about aim number 3. And aim number 3, we're going to talk about heating and cooling curves. And so the first thing that we're going to do is look at this heating curve. And a heating curve takes us through the phases from solid to liquid to gas for any substance that's heated, okay? And we're going to see that temperature is plotted on the y-axis and time or progress is going to be plotted on the x-axis. So the first thing that you should notice is that on a heating curve there are going to be 3 lines, probably should say 3 segments that are angled, and then there will be 2 segments that are parallel to the x-axis. And these 3 segments that are the ones that are going up on an angle are going to be our individual phases. And so for the first little bit here, the substance will be a solid. After it melts, it will be a liquid. And then after it boils, we will have a gas. When we are talking about a phase change from solid to liquid, remember this is melting. Oh my goodness. If I could spell, that would be helpful. Let's try that again. So this would be melting. Melting also has another word for it, and we call that fusion. We also know that liquid to gas is called boiling, and boiling is also vaporization. Please do not put evaporation here. Evaporation is not the same thing as vaporization. Now, something that we can notice is that from a solid to a liquid, as it's just a solid, the temperature is changing, and we know that temperature measures average kinetic energy. So when the temperature is changing and it's in a single phase, the kinetic energy must also be increasing, and we can say that for any of the segments where the temperature is increasing, we can say that the kinetic energy is increasing. However, if the temperature is not increasing, the kinetic energy isn't increasing. At a phase change, it's actually the potential, oh my goodness, that's not a phase change. Sorry about that. At a phase change, what we're going to see, which would be our flat lines, that is when we'll say that the potential energy is increasing. So we have an alternating thing happening here. When the temperature is going up, the kinetic energy increases. At a phase change, the temperature stops changing. That's when the potential energy increases. Single phase liquid here, temperature increasing, kinetic energy increasing. Phase change, we have 2 phases present, no temperature change, potential energy increasing. So anytime we have a single phase, we have just the temperature changing, which would be the kinetic energy. Anytime we have a phase change, we have the potential energy changing instead. Only one of those kinds of energy is going to change at a time. We also know that this is the heating curve, so energy is going to be absorbed. So this, anytime we go uphill in terms of energy, is going to be an endothermic process. If we want to look instead, oh my goodness, I went too far. If we want to look instead at the cooling curve, now the cooling curve, we can see that we are going down, so energy is being released. So we will say that this is exothermic. And whenever we're saying that something is exothermic, that means energy is being released. And again, single phases exist when the line is slanted, so gas only, liquid only, solid only. And when the line is parallel to the x-axis, those would be our phase changes. On the cooling curve, we have different names for these phase changes than we do on the heating curve. So remember that gas to liquid, we're going to call condensation. And liquid to solid, we are going to call freezing. So again, the same kinds of energy change though. We are going to have, when the temperature changes, you will have a change in kinetic energy, so that's the gas only. When the phase changes, you will have a change in potential energy. Temperature change, single phase, kinetic energy change, phase change, potential energy change. Single phase, temperature change, kinetic energy change. Because this is exothermic, we are going to be releasing these amounts of heat. Now, if you will flip back to the other one, whatever temperature melting happens at, we would call that the melting point or the freezing point. Whatever temperature the boiling happens at, that would be the boiling point. It would also be the temperature that we'd have condensation. Same thing here. Boiling point would be the temperature that it condenses and boils, depending on whether you are releasing or adding heat. The melting point here, let's try that again. The melting point here, the substance would melt at this temperature if you added heat, but it would also freeze at this temperature if you took heat away. If we just look back again at the heating curve, something to note about any time you have a phase change, anytime you have a phase change, there is an equilibrium between the opposing processes. So we are going in both directions when we're here, but we keep adding heat and adding heat and adding heat so that we get closer to the other phase that's here. But there is always an equilibrium between the two phases on either side of the phase change. So here at boiling, there's an equilibrium between gas and liquid. At melting, there is an equilibrium between solid and liquid. And I should have said liquid and gas because that's the direction where they are written. Okay, so there is an equilibrium here between liquid and gas. If we now also look at the cooling curve, at this phase change right here, there is an equilibrium between gas and liquid. At this phase change right here, there is an equilibrium between liquid and solid. So that's the end of this video for aim number 3 that has to do with the heating curve and the cooling curve. Please ask me any questions. Please send me an email, raise your hand if you're in class while we're talking about this, and just let me know that you need some help. If you don't need any help, that's great also, and we'll be moving on to the next set of questions.